Thank you, Tara, for inviting me to participate in this very interesting workshop and a discussion with some of my friends and collaborators. I'm going to be talking today about electrophysiology as a tool for global health. Therefore, considerations of sharing big data, open science, and making this available the world around are central to our concern. So, a more general point of view that speaks to what I'm going to deal with in this talk. How can neuroscience have an impact on the global burden of disease? And we know that we have neuroscience, that through neurotechnology we can do diagnosis and treatment. And that's what's known as translational research in neurotechnology. Then we ask ourselves, why is it concentrated only at the third level of medicine? Why is there a disconnect with the global burden of brain disorders? And basically, the tenet that I'm putting forward is that it is due to the fact that very little work is done to create tools or to engage with the primary health level of medicine. Of all the techniques we have for multimodal imaging, it is precisely the EEG, due to its fast temporal resolution and wide coverage, one of the ones, and also low cost, one of the ones that could be a candidate for this tool as something for global health. However, to be able to do this, I want to touch briefly on what we call quantitative EEG, about then how we can go to multinational harmonization of qEEG norms, and then to address the problem of how we have created an organization, which is the Global Brain Consortium, which, by the way, Scott and Mike Milham have participated, that wants to promote an open science platform for EEG methods. So basically, we have been working since the 70s in looking at ways of measuring the deviation of individuals from specific norms, basic to the central idea, is the simple idea of a z-score, in which we subtract the population mean and divide by the standard deviation. And very early on, after the science paper that we published with Roy John in 1977, the Cuban and New York group, we have this conception that the best way to measure this deviation is to take into account covariates, of which the most important is the age, possibly sex and others, and have age-corrected norm and sex. Now, the basic underpinning of what we call quantitative EEG, of course, is just doing the EEG recording, extracting descriptive parameters, which I will be speaking to linear parameters, which are the EEG spectral parameters. We have done and are doing work in nonlinear and non-stationary types of descriptive parameters, but I'm going to concentrate on this, which can then be these measures. Let's say the energy and the alpha rhythm can then be plotted as topographic maps of energy over the scalp. And if we pick one electrode, we can create normative data that I'll speak about a bit more. But essentially, this is the normative database. And well, this is something that comes from the Cuban Network for Clinical Neurophysiology that we created in the 90s. There's a number of publications related to this that was first to talk about how to introduce qEEG in a public health system, to work at the closest possible to the primary healthcare, how to then do what we called high-resolution quantitative EEG. But at that time, what this meant is that we would have a fine frequency resolution. I mean, there's another conception of high resolution, which is high density. I'm not going to be speaking to that at this moment. nor I'm going to be speaking about the work that we've done in source analysis. I'm going to concentrate on a simple spectral analysis because the concept that I'm saying might be generalized to other things. And well, we created norms, and here you can see the type of norms we obtained in what we call the first wave of the Cuban human brain mapping project, where we sampled from the general population in a stratified fashion. We then screened those people for that were, let's say, within a functionally healthy network, and this is what we've done for many years. We've guaranteed, since in Cuba, healthcare is totally free, so we guaranteed their treatment. And then with the people that were left, we created normative databases. You see here on the right, from a 94 publication, the energy, let's say the log energy, the log spectrum, for the different frequencies that we were analyzing at that moment, from age 5 to 97. And this is what we called at that time a developmental surface for the EEG spectrum. We then went on in a second stage to try to analyze a multimodal database. So we gathered a second set of EEGs. This here is, you see here, we're sampling the let's say the family nurse is sampling in the general population, once again chosen at random, stratified sampling. We have blood tests frozen for then subsequent DNA analysis. This is at that time a higher resolution, spatially in this case of EEG. This is a Cuban system that my team developed some years ago, and we produce our own EEG systems for the country. And then, of course, MRI. And here's more or less the sample size that we have in the normal subjects. Well, we subscribe to the idea of open science. So we have made available this database as a publication in Nature Scientific Data. I'll mention some other data sets and software that are open. I have to say that the way that we've dealt with the problem of differing standards as terms to the EEG is that we have turned all our EEG into a BIDS format. And what we're trying to do is to comply when we publish our data with any standard that emerges. I'm aware that the BIDS format is rather incomplete. It still needs a lot of work, especially on derivatives for the different types of analysis, which will take a little bit more time. It's one of the challenges. There's so many methods to do analysis. Okay, so now I want to speak to the point of what do we do if we want to do multinational quantitative EEG norms. And I'm taking this as a very simple example because it already poses several challenges. Among the challenges are, how do we get people to share data? The second problem is, how do we harmonize the differences between countries? Let's say that there may be ethnic differences, possibly. There may be problems of different levels of nutrition, and studies that we did in the late 70s and early 80s across Latin America. The single most important factor that determined changes in the EEG spectra was socioeconomic status. And then we have the problem of differing amplifiers, electrodes, and so forth. So we tried a test project that tried to address these issues. It's very simple. And the idea is based on the experience that there is that's called, that's gained a lot of interest to compare data, let's say, for the MRI. The people in Enigma have been in this, and the problem is how to have multinational studies, of which you see several there, and how to deal with what they call the batch effect. And this batch effect is something that came up in bioinformatics. There's a method called COMBAT that's being used a lot in neuroimaging, either the simplest form or let's say, a form that works with functional data. And that is something that we have the same problem. So we came across with the idea to do a multinational quantitative EEG norms study. This is the pipeline. So from several countries, we have here the different countries that participated. Besides asking for only metadata, which is country, age, device, frequency, gender. Frequency is just the frequencies at which band at which the study was done, because people cut it low and high frequencies all over the place. And what was shared was not any, besides this data, what was shared is just the cross spectrum with a program which we called Gatherer. And this program was given to people, to the different people that wanted to participate in this publication we're preparing. And they only shared the metadata and the cross spectrum. Now, this facilitated ethical approval. And I think that, people are much less willing to share raw data than to share process data. It does come up then with the problem of quality control, but we've tried to use the rest of the pipeline to control for that. We then carried out for each measure, and I'll speak to what measures we have, global developmental surfaces regarding age and the different frequencies of the frequency spectrum. We then went to look at batch-specific developmental surfaces, that is to say, surfaces like this, either for the global or for the batch effect. That would allow us to carry out, to look at the Z-map histograms, check for outliers, which we would also use nonlinear mapping. We were using T-sense and Mahalo-Loomis distance. I'll speak to this later, to find outliers. And then with correction of outliers, we would go to produce finally the global and batch specific surfaces. I have to say that this process had to iterate several times. Sometimes some of the people that participated gave us the wrong order of electrodes. We were using the 1020 system, and we would find it through the outlier detection in this multidimensional space. Now, these are the countries that participated. It is 9 countries. There's 16 data sets. This is really not what we would like. It's about 1,700 subjects. There is a diversity of countries and of equipment, but not as much as we would have liked. The pre-processing and analysis, as I said, was based just simply on the 1020 system. We did not want to do anything more. People like our own second wave Cuban human brain mapping data, we downsampled the 19 because this was just testing the whole methodology. We get rid of the average reference. We eliminate a global scale factor. And then we carry out 2 things. We either have the long spectrum, or since we want to do not only the information of the spectrum, but also we want to do the information related to the cross spectrum. And the cross spectrum sits in a Riemannian space of positive semi-definite matrices. We carried out a transformation in which we vectorized and took to Euclidean space a set of cross-spectral matrices. This is the result after harmonization, and here we see that we get essentially the same results we had demonstrated now for the full data set. And down here, these curves are just at different ages, where we see the usual diminution of theta, transition to higher alpha, and then regression with age. And it's the same thing now for the full data set as for the study we did in the 90s in Cuba. This is an example that if we only look at the log spectra, here on the left, we have the TS and E nonlinear map of all the data. The log spectra doesn't seem to need a batch correction. Here we have the Mahalo-Loomis distance and the robust Mahalo-Loomis distance. We don't see outliers. It's pretty homogeneous. However, when we put in the Riemannian transformed data, that is to say, in an Euclidean space, the cross-spectral information, then we do see a strong batch effect. And in fact, there's a tendency for more outliers. This is the model we used. It's based on functional data analysis using Naradaya-Watson kernel regression. And it's essentially an ANOVA decomposition that takes into consideration factors like frequency, sex, global batch effects. I'm not going to go into details. And we then went on to do outlier detection using both the Mahalanob's distance versus the robust distance. We would find certain outliers, and that would allow us to go and check back without people having to show us their data. This is what happens when you look at the full data set after taking out the global tendencies without batch correction. It's pretty good, but you still see that there's some batch effects, and that improves considerably after taking out the batches. Finally, I want to say that after we did the following. We have a test data set, which is a group of children, which, by the way, we followed, with Harvard. There's a long-term study called the Barbados Nutrition Study, in which subjects have been studied from at age 5, and then we recorded the EEGs again at age 45 years later, at age 50. Now, we just took the age 5 data set and compared it against the norms using the Mahalanob's distance. And what we see, if we only look at the log spectra, we get a significant, but not that impressive AUC. If we then use the full cross spectrum, it increases a lot. And if we do batch correction and also a method called contrastive principal component analysis, we get very good discrimination. So these issues of harmonization are important in making, let's say, normative data use. Finally, I'd like to finalize in a few minutes. The Global Brain Consortium is following up on a meeting that we organized in WHO headquarters in 2016, which has followed up with a special issue of Neuroimage that's coming out. But the Global Brain Consortium is trying to promote activities and to promote initiatives that will deal with global health and EEGs at the center. In fact, Scott and Mike have participated in this. We have several work plans. I'd like to mention that as a consequence of this, there's a new project that's called qEEGnet. This is a project that Alan Evans wrote in the name of Canadian investigators and others. And this grant will develop several things that are, I think, very interesting in terms of the discussion we're going to have. We base our work in this sense with the Canadian Open Neuroscience Platform based on Loris and Sebring. And we've created what we call the CCC Neuroinformatics Platform. This is Cuba, China, and Canada. And we've made available a number of data sets. So for the first wave of the Cuban brain mapping data, that's totally open, as is the second wave. But this is only EEG cross spectra. And also we've developed software to do both surface and source quantitative EEG analysis using frequency analysis. This is also on GitHub. It is a separate. So to summarize, I've spoken about what we call quantitative EEG, which really should be called linear, stationary, quantitative EEG. Then we've spoken about an experimented harmonization of multinational qEEG norms of this sort. And then I've spoken to the problem of how the Global Brain Consortium is providing an open science platform in coordination with the Canadian Open Neuroscience Platform and is eager to look for collaboration. I can speak in name of both Alan Evans and myself that we're eager to collaborate and look for joint projects that might really make EEG the tool that it should be, to be used to have an impact on the lives of people around the world. Thank you very much.